Hey guys, welcome to another video on UHS chemistry physical part, and this video is specifically for A-level students to help them slide in the FSC mindset, to acquaint them with the sort of questions that come up in the NUMS and the MDCAT exam and the sort of material that is often tested. So the correct representation of the delta H naught F of NH3, and this is obvious. This is incorrect because formation is from elemental state, and this is wrong because it is not balanced. This is correct, elemental state and appropriate balancing. The internal energy is the sum of the kinetic energy and the potential energy. If the internal energy of a system increases, then all of the following changes may take place, except the state of the system may change. That is possible. The temperature of the system may change, also a possibility. The chemical reaction may take place. Again, it's a possibility. The root of the system may change. Now that is a bit ambiguous. The root of the system may refer to the mechanism followed by a particular reaction, and the mechanism is not altered by the temperature or by any external influence, with the exception of the addition of a catalyst. As such, T is an improbability. So which of the following has the higher value of delta H? Lattice. Now this is a good question because the value is dependent on two factors: the size of the cations and the anions and the charge. So +1, -1, +1, -1, +1, -1, +1, -1. The charge is the same, so what is most impactful will be the size. As we go in this direction, the atomic size falls and it appears to increase in this direction. Cesium is right at the bottom, whereas lithium is somewhere over here. Cesium is at the bottom of group 1, whereas lithium is at the top of group 1. So comparing these, lithium fluoride will have the higher lattice because of the smaller size of the lithium ion. And then we compare NaCl and KCl, and I believe NaCl is the second element in group 2, and potassium is the third element in group 2. Sodium is in the second period of group 1, and sodium is the third period, lithium is in the second, and potassium is in the fourth. So comparatively speaking, again, it's pretty obvious that lithium fluoride will have the higher lattice because it's topmost, and as such has the smallest size, and they all have the same charge. That is a constant, so it will have the highest lattice enthalpy. They have actually given a couple of values of the lattice enthalpy. I think they've given for potassium chloride, and that is about 690. And these are these numerical values which A-level students, and they don't have a habit of learning. We just tend not to do that because they don't come up. It's not a sort of question we remember, but they're often asked quite frequently, and as such it's a good idea to remember them. For example, the lattice of formation of NaCl is -411. That is something quite worth remembering. And there are other stuff such as the formation of potassium chloride, and that was actually, I think, that was mentioned in the chemical bonding topic, and the lattice enthalpy was given a value of 690. And you should know that lattice enthalpies, they always have this negative value. So you need to remember the formation of KCl because that is given in the theory and is very much likely to come up. And that is the formation of NaCl. And another important thing about lattice is that it's always the heat of reaction. When the gaseous elements or the gaseous signs, to be more correct, they basically form the solid lattice. So some stuff about lattice that is important. The values in the table are less important, but they do sometimes come up, but I guess it's a waste of time trying to learn all of those. So getting just a main idea of their relativities is a better choice. So when a strong base is treated with a weak acid, then neutralization is, it ought to be less than 57.4 because some of the energy will be used up to further ionize the weak acid. If a chemical change takes place by several different routes, the overall energy change is the same regardless of the route by which the chemical change occurs, provided the initial and the final conditions are the same. And this is in accordance to the law of mass action, Joule's law, or Hess's law. This is a direct statement of Hess's law. So which of the following is extensive property? Is it density? Is it pressure? So, or is it something else? And before that, I found another topic. And that is from not from the chemical bonding topic. This is from, I think, the energetics topic. And in that one, they gave a couple of cycles, and in that they gave the lattice enthalpy of sodium chloride as being equivalent to negative 787, whereas delta HF is equivalent negative 411. Two very important values, and you have to realize that if you have the delta HF values and the values of atomization, ionization, electron affinity, to get the answer you simply have to add those two up, and the value that you will get will be the delta H lattice. In addition to this, extensive property is something I did not find written anywhere in the book, but if I missed a page and you know about it, please comment. So an extensive property is a bulk property, meaning that it is a physical property of a system that is not dependent on the system size or the amount of material. So it's something that is just innate to the system. For example, the ratio of an object's mass and volume, that is density, the ratio of an object's mass and volume, which are two extensive properties, is density, which is an intensive property, because extensive is something that is changeable. If you talk about density, it's going to be the same for a particular gas system no matter the condition, because that is something that is sort of like innate to it. The same may not be applied to pressure, temperature, or enthalpy. So an intensive property is one whose magnitude is independent of the size of the system, whereas for an extensive property, dependency exists. Others can be temperature. The temperature is something of an intensive property. Refractive index, density, and hardness, all of these are intensive properties. Temperature is cut, density is cut. we're left with either enthalpy or pressure. So when we cut a diamond, the pieces maintain their intrinsic hardness. So hardness is independent of the size of the system. Pressure is also an intensive property because pressure is usually uniformly distributed. Mass and volume are in extensive properties, but they're not over here. Another intensive property may be boiling point because it is independent of the amount you have. Concentration is intensive, density is intensive, melting point, boiling point is intensive, pressure is intensive. So the extensive property is enthalpy. So the enthalpy of formation of a compound is always greater than 0, can be greater than 0 or can be less than 0, yes. Always less than 0, no. Is 0 at standard state. This is only applicable for the formation of an element, can be both positive or negative. And lattice energy is very useful in discussing the structure of ionic compounds. The properties of an ionic compound are the strength of bonding, so which is correct. When we talk about lattice energy, it is a direct indication of the strength of the bonding. About properties, there is definitely a distinction between them. So 2 and 3 are a must, and because there isn't anyone that contains 2 and 3, so we're going to have to go with 1, 2 and 3. And I guess it is somewhat indicative of the structure. A bomb calorimeter is usually used for the accurate determination of the enthalpy of combustion, formation, neutralization, solution. The answer is combustion, and this is actually written in the book. So let's proceed. So the heat of formation for CO2 is, so the formation energies are written in the book in a lot of places, but if you don't remember, let's look at it. The heat of formation should probably be exothermic because this is sort of like combustion. So I guess we can negate these in good faith. Because the more probable answer is, improbable answer is this one. So it's minus 390, minus 394 and minus 294. In certain cases it's a lost cause if you cannot remember at all, and because this is these options are not telling us anything. So I think this was actually given within the same chemical energetics topic. Let me look for it so I can inform you as well as to its exact location. There are such values precisely in the chemical energetics topic, and some values can be found in the chemical bonding topic, and these are the two chapters in which most such values are found. And the answer is negative, or is it positive? It's positive 393.7 kilojoules. It's negative 393.7 kilojoule per mole. So it's negative 394. And this is indeed in the chemical energetics topic. I know it's really hard remembering all of these values, but at this point we don't really have any other choice. You can find different types of mnemonics or memory markers to help you remember stuff like this. Now if at this point you had remembered that the value was positive or negative, that would have been a great help. It's obviously negative, but what negative? These are very close together. There could have been quite the confusion. CO2. One way you can remember is that there are 3 atoms, 3, and then there is a multiple of 3, and 4 is comparatively easy to remember when you've gotten the other stuff down. Anyways, let's proceed to the next one, and this question is really emphasis on why it's important to remember, because these are 5 marks. It's a stupid question, but it's going to be worth 5 marks, and we cannot do anything about that. I often mess up the most in these questions. So all of the following are state functions except work, heat. I guess this is Gibbs free energy, and this is enthalpy. Now Gibbs free energy is indeed a state function. Enthalpy is also a state function, but if this is work, this is not a state function, because work is not a property of a system. It's just what you're doing to it. So which of the following has the greater bond energy? Now in generally speaking, the more bonds we have, the greater the bond energy. And because after carbon we get nitrogen, that means nitrogen has a smaller size, not to mention, and so a smaller size is likely to have a greater overlap and a greater bond. And in this case you're indeed right, because so there are some values of the bond enthalpy values that are really important. Among them are the NN values, which is about 411, because we have a whole chapter dedicated to nitrogen, so it seems fair you should know those values. And CC is important because C, you should have an idea of the value of the C single bond C, C double bond C, the C triple bond C, and also the halogens. These are one of the more important ones. So if we take a look at the actual values, this is actually kind of also important because it's written in the theory. It's 1072. And the reason for that would be because, no, my apologies, this is C single bonded O and C triple bonded O. So nitrogen triple bond, so what is the value? You can find these values in the chemical bondings topic. I would suggest you don't try to remember all of them. That is something that's likely to backfire on your head pretty badly. Anyways, see, this obviously is comparable. So if you take a look at the table, some important values you should know that 436 is the bond enthalpy of HH. That is important. You should know that the bond enthalpy of CC, that is C single bond C, is 348. You should know the value of the FF bond is about 155, that of CL is 242, that of II is 151, That if Br is about somewhere in the middle, 193. You should also know that the value of the C double bond C is 614. That the value of C triple bond C is 839. You should also have an idea of the bond lengths, but this is fine at this scenario. And as I've mentioned, the value of the C triple bonded O is 1072, and that is literally in the theory part of it. So definitely something for you to remember. The N triple bonded N is 941, and as expected is the one with the greatest bond energy, because this molecule is literally, it's fabled for its unreactivity. So guesswork is something you can subsist on for this question, but it's a good idea to have some idea of the values. If you know of C single bond H as being about 413, and so being slightly higher than C, the single bond C is also a good idea. The fact that CO is 358, not a bad idea to remember. And C double bond O being about 799. Anyways, let's proceed. If you have the time to actually write down a lot of this stuff, it's good, because memory, that's the way our memory works. If we have stuff written down, we tend to remember, because we remember having written that stuff down, and we're like, that is important, and our brain remembers that. Like the relative strengths of the dipole-dipole bonds and the HH bonds. If you don't write it down, you're liable to forget it the next time around. But if you wrote it down the moment you saw it as being, you recognized it as being important, the next time you will look at it, it's very unlikely that you will forget. So in exothermic reaction, the heat contents of the products more than that of reactants, reactants more than that of the products. This is it. This can literally never be the case. Chemical reactions that release energy to the surrounding are described as exothermic. In an exothermic reaction, the temperature of the surrounding increases, understandably so. And all of the following are examples of exothermic reactions except combustion of fuels, reaction of sodium with water. Now photosynthesis is endothermic. Enthalpy is the total energy of the material that react, and all of the following statements are correct except enthalpy of a system is not measurable, but delta H can be measured when heat energy is exchanged. This is correct. Symbol delta is often used to measure a change. Yes. The unit of delta H is kilojoules per mole. Yes. This is wrong. It's actually the opposite. It's products minus reactants. So all of the following factors, they work to increase the bond energy except the electronegativity difference. Yes. The electronegativity difference increases the bond energy. The S character also increases the bond energy. The bond length actually has an inverse relationship. So if bond length is greater, what does that mean? That means that the energy is less. It's an inverse relationship, not as much of a causation as it's a correlation. And bond order is the number of, like if it's for a CC it's 1, for C double bond CH2, that kind of thing. So this also has a direct relationship. So the answer is B. Next, by applying Hess's law, you need to calculate the enthalpy change for the formation of an aqueous solution of NH4Cl from NH3 gas and HCl gas, right? So enthalpy of formation of an aqueous solution of NH4Cl. Alright, so how do we do that? Well, we can compare these. So if this is going in this direction and this is going in this direction, and these two things, they are sort of going in this direction. To figure out what the value is, what you do is you just have to realize one thing, is that formation of an aqueous solution of NH4Cl from NH3 gas and from HCl gas. The value they've given is for the aqueous. So if we turn these around, like invert this and invert this, or actually in this manner, these actually kind of cancel out. If we attempt to combine these, this will cancel out, this will cancel out. So you'll be left with just these and this. So you just have to add these up. Simple addition: 35.16, 72.41, 51.48. So the answer is 5, 6, 7, 8, 9, 159.05, and this is from simple algebraic addition. With the increase in the size of the anion, which of the following ionic compounds has minimum lattice energy? So we talk about this. We have F, we have Cl, we have Br, we have I. The minimum lattice energy will be the one that is the greatest atomic size, and so the answer will be sodium iodide, because this is the highest, it's the biggest one, and so the same charge is just spread over a larger distance. Which of the following reactions does the value of delta H naught represent both the standard enthalpy of combustion and of formation? Not this one, because we need to start with the elements. Definitely this one. Not this one either, because carbon in under physical 98 Kelvin and 273 Kelvin, and STP basically it doesn't exist in gaseous format. So this one is correct, because elements are in their physical state and combustion must produce CO2. So all of the following statements are correct except. So we look over here. Delta H naught solution is the enthalpy change, is the amount of heat absorbed or evolved when 1 mole of a substance is dissolved in excess solvent. This is actually true, and they've given two values of delta H solution. In the book, they've given for sodium carbonate, which is plus 25, and they've given for ammonium chloride, which is negative 16.2. So this is correct. Combustion is the enthalpy change when one mole of a substance is burnt in excess air. That is also true. And they've given the enthalpy of combustion of carbon, which is 394. The exact value they've given is 393.7. And in addition to this, they have given the value of combustion of ethanol, which is about -1368. And one thing to remember about combustion is that they always have the same value. And they've also given for atomization and neutralization is the enthalpy change when 1 mole of gaseous atoms are formed from its compound under standard conditions. Here is the error. They need to be formed from the element and not from the compound. And they've given atomization values for hydrogen. They've given atomization values for sodium. And the atomization value of hydrogen is 218, 218, and all atomization values are positive, something worth remembering. They've also given for sodium, I think. And what is the value for sodium? The atomization value is, I don't think they've given, I think they've just given the ionization. But because sodium is such a frequently asked, you can say it's something that often comes up, is one of the more common ones. Could be a good idea to see because it's probably somewhere in some table and you should know what the value is. Yes, it is given. The value is 108. So for hydrogen, the atomization of hydrogen was 218, and that of sodium is 108. So it actually takes less for sodium to be converted from its into its atomized format. So atomization of sodium is 108, whereas that of H is 218. So two really important atomization values. Now neutralization is always has the same value of -57.4. The enthalpy change when 1 mole of water is formed by the reaction of 1 mole of H plus from an acid with 1 mole of OH minus from a base. So plus 108 for Na and plus 218 for H. And for a combustion we have for ethanol, which is -1368, and we also have for carbon, which was I guess it was about 393.7, and combustion is always negative and atomizations are always positive. They have, I think they've also given, yep, over here, this one is it, this one is 394, and this is actually the formation for monoxide, and this is the oxidation of the monoxide. There was this cycle in the chemical energetics topic in which we went from C to O2 directly, or from C to carbon monoxide, and then from carbon monoxide to CO2. So the values are given, so maybe you should be a bit acquainted with them. So for the formation of 1 mole of carbon monoxide, the enthalpy is -110, and the formation of, or the oxidation of carbon monoxide is about -283. These are more minors and not as important values, but they do have the chance that they will come up because it's written in the theory portion. So the enthalpy change of formation of gaseous ethene and gaseous ethane are 52 kilojoule per mole and 85 respectively. So what is the enthalpy change of reaction at 298 Kelvin for the following process? So if it takes this much, so if we start from the same amount, say we start from 2C and we start with 3H2O and we go over there, or we go over there. If we go over there, we get a value of, we use 52, and in this direction it's positive 52 over here and negative 85 over here. We don't have to worry about these because this is an elemental state and they have a value of 0. So it's 52 over here minus 85 over here. So if we go from here to here, we get the answer. So the sign is reversed, it becomes negative 52 plus negative 85. So it's about 137, negative 137. The signs are pretty important. The energy of the reactant is not equal to the energy of the product. Thus, the difference of energy is in the form of, is it in the form of heat energy, chemical, or light? It's usually in the form of heat energy. The heat of reaction may be positive or negative and can be determined accurately by using calorimeter. When a system undergoes a change, which property is unchanged? The mole, the atom, the molecule, or the activation energy? The activation energy is the minimum amount of energy you need for a reaction to proceed. So a system undergoes a chemical change. The number of moles might change. The atoms obviously cannot change. There will be rearrangement, but it's unlikely the atom will become another one unless the change happens to be radioactive. Activation energy might change because now we have a different position, we have different elements, and whatever reaction they are capable of proceeding with, even if it's a backward reaction, will have a different activation energy. So the atom is a likely option. Molecules are a combination of atoms and are subject to change. An equation which indicates the physical states of the reactants and products in addition to the numerical value of the heat of reaction is called, so both the physical states and the numerical value of the heat, so that will be a thermochemical equation. So in which case the delta H is negative. Now this is the atomization. The atomization values are always positive. This is ionization, first ionization, and first ionizations are also always positive. You need to give in the energy in order to take something out. And the ionization value of Na is of supreme importance. And it's positive for 96, and it's the same as the bond enthalpy of hydrogen molecule. And this over here is half the bond energy, so it should be 282 divided by, or 242 divided by 2, because we talked about this, right, about the bond energy having a certain value. I think we have studied this one in the chemical bonding topic. They have given 242 in the theory as the bond energy, and for one molecule it's half of that, so it becomes 121. This is the first electron affinity, and the first electron affinity is always negative. The second electron affinity is on occasion has a negative value, positive value. This for in this particular example the answer is negative 349. I know these are a lot of values to remember, but if you try and get an idea of a lot of them, and in case they come up, it will be really beneficial to you. So which of the following is a mathematical expression of the first law of thermodynamics? This is it. delta E is equal to, this is the internal energy, this is the heat content or the heat energy that is given or taken out, and this is the work that is done. This is completely different. This is the relationship between delta H and Gibbs energy, and I think this is the heat capacity, and this is just a rearrangement. Which of the following is not standard condition for thermochemical measurements? A pressure of 1 atm, that is the standard condition. A temperature of 0 Kelvin is wrong. We take 0 degrees Celsius or 273 Kelvin. And substances are in the normal physical state for these conditions. Yes. And concentration of unit activity is effectively 1 molar. Yes. So using the information given in tabular form, you need to calculate the delta H lattice. There is a simple formula. You simply have to add delta HF and the sum of all of the energies. So this is the enthalpy of formation, which is negative, and this is we're going from K solid to K gaseous, and so this is the enthalpy of atomization of potassium. The first we have the first ionization energy, which is similarly important. Then we have the second. Then we have the electron affinity of bromine, the first, and also the half the value. So you should know this value for bromine, because bromine is pretty important. So you need to know basically what the amount of energy is needed for this state change to take place. And also you should be aware of what the value of the first ionization of potassium is. It's 419. It's written over here as 420, but in the book it's written as 419, and it's vastly important. Anyways, for this question you simply have to add all these values up while being really careful that you don't mess up on any of the signs. So first of all, let's add 420 plus 90 is obviously 510, plus 112 is 622, and then from that if you add minus 242 and minus 392, it becomes minus 714. So the overall is going to be negative, and it's going to be about, maybe we've messed up at some point. This is the value of, this is the atomization, this is the ionization, this is the amount of energy that is needed to go from the liquid to the gaseous state. But what they have not mentioned, they have skipped on, is the half of the bond enthalpy. We have done this is about 179 or 193, and this is also in the chemical bondings topic, and it's positive 193. So it's the half of that which is relevant. They've actually skipped on that. So it's negative 92. And you're going to have to add that. So the important thing about this topic is that you have to be careful with all of the additions. On the last topic of the chemical energetics, we have this formula delta H lattice is equal to delta HF plus delta HX, and the HX often comes out as being negative, except in this case we have to reverse all of the values that we've gotten. So what we got from the addition was 622, which happened to be positive, and from the other one we got minus 714. So this is a bit problematic. So the problem has been resolved. What you have to do is you have to add these up, and then you have to minus these from this. So that is how you will get the answer. We had a bit of a problem over here, but it's been resolved now. So this particular formula that I've used is found in thermochemistry topic. And we're in thermochemistry topic, I believe it's one of the last pages. It's on page number 209. It's given as delta HF minus delta HX, and delta HX is delta H80 plus delta H ionization plus atomization of the other one and electron affinity combined. So it's a sum of that, and it's really important. So delta H lattice is equal to delta HF minus delta HX. So which of the following relation is not possible? So delta E is E1 plus E2 plus E3. Delta H is delta H1 plus delta H2 plus delta H3. Whereas delta H is equal to delta E plus P delta V. And the other one is Q is equal to Q1 plus Q2 plus Q3. And if you take a look at the thermochemistry topic, in the starting ones they've given some expressions like delta H is equal to delta E plus P into delta V. So this is all right. This is completely fine. And they've given that either you go this way or you go that way. It should be the same. And it's also the same for delta E, because irregardless of the route followed, the sum ought to be the same. But Q is heat, and heat energy is, unfortunately, it's not a state function, and so we cannot have this. All of the following enthalpy changes have positive or negative values, except lattice always has negative, and A might be for atomization, but I'm not 100% sure. This always has a negative value, can have positive or negative. There are some important values of delta H formation that are mentioned from the book. There is the formation of NaCl, which is negative 411. There is also the formation of magnesium oxide, and I think this was from the chemical bonding topic. And the value of this formation is 690, negative 692. Negative 692 is the formation of magnesium oxide. There is a formation of water, which is minus 285.58 or minus 286. These are important formation values. Let me see if there's something else I've missed out. These are pretty much the more important ones they've mentioned, the ones you should try really hard to memorize. There's also the formation of the enthalpy of formation of CO2, which is about negative 390.94. That is also an important formation. So magnesium oxide and carbon dioxide and water, they are the important ones. Magnesium oxide is minus 692, it's negative. Water is minus 286, it's negative. CO2 is minus 393.7 or minus 394, which is also the same. So all of the following are endothermic reactions, except this is actually what happens in the sulfur in the contact process. You need to remember the value. It's like negative 255 or 256. And this conversion of N2 plus O2 is actually, I think it's a positive value, and it's written in the energetics topic. This is about positive 181, and this is also an important formation value, positive 181. The others one we discussed were all exothermic. Now this is rusting. Rusting is in general negative, and formation hydrogen iodide is also negative. The value is perhaps written somewhere in the book, but this is definitely positive. This is definitely positive, because this is definitely negative, and we're sure that this is positive, so this one must be negative. And this is negative because we have also done this, so we are assuming that these two must also be positive values. Now if you're curious about what the actual value for the sulfur is in Punjab textbook 2, this on the chapter, I think it's group 5A and group 6A, 656, they have given the contact process, and they've also given some of the properties of sulfur, though you don't really have to do the properties. And the answer, or the enthalpy change we are interested in, that is the enthalpy change of formation of production, is when 2SO2 plus O2 form 2SO3, the relevant energy change is minus 269.3, and remember this isn't for one molecule, this is for two of them, so you have to take the half of it, the molar enthalpy value. And as a side note, what are the conditions? You need 400 to 500 degrees Celsius. The pressure has unfortunately not been mentioned. So the heat content of a system is the enthalpy. The second name has been mentioned in the book. So which of the following is an exothermic? Combustion of ethane, combustion is always exothermic. Decomposition of water, well, the formation of water was negative. It had a value of 285.58, negative 285.58, so the reverse will have the same magnitude but different sign, so it will be positive 285.58. So no. Electrolysis of molten NaCl, electrolysis is always a non-spontaneous reaction, and so is always positive. Conversion of graphite into diamond, because graphite is the most stable form, this conversion into a less stable form will require the input of energy. And this fact was actually mentioned also in the chemical energetics topic, and also in thermochemistry, I think. If you go to page 195, they will have probably given you values for graphite. They've given the delta H for graphite as being minus 93.7. So the value of delta H for the process represented by the equation is equal to the first ionization of K, no, because for that it would have to be in the gaseous state. The first ionization plus the first electron affinity, no. The atomization plus the first ionization, definitely, because when atomization happens we go from the atom in the normal state to the element in normal state to the gaseous atom. So if we take this and we also take this, because then firstly it would have to be converted in this form and then it would have to be converted in this form, so D is the relevant one. So which one of the following is involved in determining the enthalpy change in chemical reaction? The number of stages involved, the activation energy, the initial and the final states, definitely. Is the mechanism really involved in determining the enthalpy change? Well, if you know which mechanism is relevant, it would help out. Let's talk about this in the end. Heat of neutralization can be determined by bomb calorimeter. Traditionally speaking, no, we usually use the glass calorimeter. Which of the following is the application of First Law of Thermodynamics? To study process at constant volume, to study process at constant pressure. So the answer is both A and B. When the pressure is constant, all of the heat that you've given is equal to delta H, and when the volume is constant, all the heat that has been given in is equal to delta E, where E is the internal energy. And these are both applications. Is buried in a bomb calorimeter. Temperature recorded is 6 Kelvin. Calculate the enthalpy of combustion if the heat capacity of the calorimeter is 100 kilojoules per mole. This is also, in my opinion, really interesting. The heat capacity. We have this formula m into s into delta T, and this is equal to Q. So mass is 24 gram. You don't have to change that, normally speaking, but a good idea to convert to kg. 24 in 10 power minus 3, because while gram is alright for mole calculations, this isn't a mole calculation. S is unknown. T is 6 Kelvin. S is 100 kilojoule per mole. So its mass 24 in 10 power minus 3 multiplied by 100 in 10 power 3. So the 3's and minus 3 plus 3 cut out. 6 into 100 is 600 in 24. And because this is just for like 24 gram of graphite, and we know that one has like 12 gram. So this is for like 2 moles, and half the value will be for molarity. So we divide by 2, it becomes 600 into 12. And the answer is really complicated. Let's do this again. We know C12.6 is what makes up graphite. So, and we also know that M into S into delta T is important. So they've given us the heat capacity of the calorimeter, and this is not the specific heat capacity, this is the heat capacity as a whole. So you don't need to put in the M value, it's simply 100 into 6, which is 600. And you have to divide by 2 because 24 gram is equal to 2 moles, and we want the value for 1 mole only. So there is this equation given in the book, which is S is small c into delta T, and this small s is basically the heat capacity of, and if it's specific heat capacity only, then you need to take the mass into account. So now they're asking which of the food has greater calorific value. I'm a bit unsure if this is written anywhere in the book. If it's written and I haven't found it, please tell me. So ghee is like unlikely because it heats up really quickly. Honey is a possibility, but honey often decomposes. Milk or egg. So I think when we boil milk, is it the one that boils for less heat, or is it for egg? Because we boil both of these. I think egg is the one with the greater calorific value. That I'm not 100% confirmed on this one. So which is involved in determining the enthalpy change? The number of stages involved in the reaction. Well, not directly. The activation energy can be used. If you have the activation energy of the backward and the forward, you can figure out the enthalpy change. It gives like this, and you know what this is, and you know what this is. You can figure out what this is. Mechanism is also involved, but if you're going, since all of these seem alright, the least likely is activation energy, because it hasn't been mentioned if we have access to both the forward and the backward. So this is it. Hopefully you found this to be helpful. If you did, please like and subscribe.